Hey guys, this is a follow-up video to Leetcode problem number 127 word ladder. So if you guys were following previously, I made a live video of me solving this problem live. However, in that video, I only managed to get to a brute force solution, which was not optimal enough um, to be able to be submitted through the Leetcode system. So in this video, I just want to quickly go over the solution um, that I have found and researched. So really, just to recap, word ladder. So just to quickly talk about the problem. So the problem the problem statement is that we are given two words, begin word and end word, and also a dictionary's word list. We have to find the length of the shortest transformation sequence from begin word to end word, such that only one letter can be changed at a time. Each transform word must exist in the word list. And also note that begin word is not a transform word. So really what that means is that begin word hit, end word cog, for example, we have to find the shortest, essentially the shortest path from this word to this word. And the words within this list are sort of a stepping stone, or if you can think of another way of thinking about it is you can think of it as the a sort of a steps, right? What are the steps needed to take to transform this word to this word? So for this example, we are changing the word hit to hot. And again, we can only change one character at a time, right? So we're changing from I to O, from H to D, from T to G, and finally from D to C, right? And as you can see, each transformation, each word, each step are contained within this list. So that's really what the problem is asking us to do. We have to find the shortest sequence of change, right? That will result in the end word. And all of the changes, all of the steps or intermediate words essentially has to exist within this list. Okay. So really the approach that and really the way to think about this problem is to convert it into a sort of a graph problem, right? If we were to plot this out into, if we were to project this into a graph, right? The edge, so let's say from this word hit, the only words that this word can be transformed to within this list are hot and dot, right? By changing one character. Remember now that we can only change one character at a time. By changing any one of the character within this word, we can change into either hot or dot, right? So if you were to imagine, we would have a graph, and where the word hit would be a node, hot and dot would be another node, and we would have an edge connecting between the two nodes, and so on and so forth, right? Nodes. And so essentially what I'm trying to say here is think of this problem as a graph problem, right? And what I'm and a node essentially are connected if and only if node A can be transformed to node B by changing one of the characters in A, right? Okay, let me rephrase that. Two nodes are connected or reachable, meaning node A and node B are neighbors if and only if node A can be transformed to node B by changing one of the characters in A or in B, right? So once we can think of this problem as a graph problem, it really boils down to pre-existing graph traversal algorithm. And one of the algorithms that we can rely on is breadth first search. Once we convert this problem into a graph problem, really all that we have to do is, since we know the starting point in this word is the word hit, and we know the end point, which is the word cog, really all we have to do is we have to explore all of the nodes within this graph, and once we hit the final node cog, then all we have to do from there is we return the distance that we have traveled since coming from the word hit, from that node hit, right? So essentially we just do breadth first search. And you might be wondering, why do we do breadth first search? And the reason for that is, simply put, we want to explore neighbors level by level. If you were to imagine, okay, essentially the reason why we don't want to do depth first search is because we don't know. Let's see, what am I trying to say here? Because we are doing it by level in breadth first search, any first nodes that hit the word cog, essentially we are considering all the paths equally and at the same time, and that is why breadth first search is best for this problem. And any path that hit the final word first will be the shortest path, right? Because we are traversing all of the path at the same time. I hope that explanation makes sense. If you don't fully understand what breadth first search does, I highly recommend googling it. And yeah, okay, so we know for sure that breadth first search is an O of n algorithm, right? Another tricky part about this problem is understanding the number of edges between two nodes, right? And what do I mean by that, right? From this word, how many possible edges are there, really, right? Because we can only change one character at a time, there are 3 possible nodes that can be connected to this word, if that makes sense, right? Okay, let me say that again. Okay, that's not. Let me rephrase that. Because, for example, the number of. Okay, let's see. Okay, so this is what I'm trying to say here. The number of words, if you were to imagine this as a graph, right? The number of words that can be, for example, that can be connected to this begin word hit, for example, is 24 times 3, right? And 3 is the length of this word, right? We have 3 character, and I'm sorry, 26. There are 26 alphabets in the English language. Okay, there are 3 characters within this word, right? And we can change, for example, we can change each one of the character into any possible character within the English language. So really what I'm trying to say here is what I'm trying to formalize here is there are 26 times length of as essentially possible nodes, possible edges, right? And because there are no duplicates, this is true. Okay, so keeping that in mind, okay, so another thing that we have to do is we have to somehow generate, once we know the algorithm that we have to use, which is breadth first search, now we have to generate adjacency, some sort of an adjacency list, right? Meaning with this word, what is a list of its neighbors, right? And we know beforehand that for this example, the neighbors of the word hit are hot and dot. And in order to make things easy, what we can do is we can we can use a hash map, right, to associate a word to some sort of unique key. And as I was saying earlier, there are 26 times length s possible edges, right? And each one of the changes of the character, meaning, so let's say for the word hit, right? So this asterisk can be any character. So by itself, we can use this as a unique key. Another unique key here is that and that, right? And what we are potentially doing here is associated with each of these unique key. What are the words that are associated? What are the words that can be transformed into by setting the asterisk character, right? So by doing this, what we'll get here is we know that by changing the first character of the word hit, we'll get let's see, by changing the second character, in this case I, right? By changing I to O, what we'll get here is the word hot. By changing the first, I'm sorry, actually hit can be transformed to either hot or, let's see, what else can it be transformed to? Actually hot is the only word that hit can be transformed to. Okay, I'm sorry about that. Okay, so that's our example, right? So essentially we're creating hash maps of what possible hash how do I explain it? Essentially what I'm trying to say here is once this hash map will help us identify neighbors of the word hot, right? By, as I was saying earlier, there are 26 times length of s possible edges. And what I'm saying here is that for each one of those changes, for each one of those character changes, we have 3 characters here. What are the words that we have within this list that are associated with that transformation? In this case, if we were to change the first character to anything at all, there's no neighbor for that, right? There's no words that can be transformed into by changing that first character. However, by changing the second character to O, the neighbor of the word hit now is hot, right? So now we have hot within as one of our neighbors for this word. And now by changing the last character T is nothing, right? Let's do another example just to get the point across. So this is neighbors of hot. Guys, thanks for being patient. I know that a lot of times my explanation can be a little murky, so it is something that I'm still working on. So please be patient with me, and if you have any questions or anything at all that I can help you answer, just message me or just put it down in the comment below. Okay, so let's do another example. Neighbors of, let's do another one here. Let's do hot. So now let's do hot. Okay, sorry, this is neighbors of hit. So now let's do neighbors of hot. And what are the changes? So as always, because this is a 3-character words, we can either change the first character, the second character, or the last character, right? So by changing the first character to any one of the 26 alphabets, what are the words that exist here that can become one of the transformation? So in this case, if we change it to D, then we'll have the word dot, right? If we change the first character to D, we have dot. If we change the second character to let's see, what can we change it to? There's nothing, right? If we change the last character to, there's nothing still. Let's see, what can we change it to? What else can we change it to? Oh, another one here. So we can, if we change the first character to D, we get dot. If we change the first character to L, we get lot, right? Okay, so I hope this sort of makes sense. And so essentially what I'm trying to say here is that in order for us to effectively utilize breadth first search, we have to be able to somehow generate neighbors of each word. And we do it by generate an adjacency list where the key are the possible changes, right? And the problem, and within the problem statement, we can only change one character at a time. And so I have a general and so the general form that and the number of changes, possible changes, is 26 times length of S, right? So those are possible edges, and so we essentially what we have come up with is a list where we put an asterisk in front of the character that we change, and then we put any words that can be result of that character change into a list, and so on. And so after generating this adjacency list, we can finally utilize breadth first search, right? And if you remember from studying algorithms, breadth first search is an algorithm that utilizes a queue, and as we visit the neighboring nodes, we mark them as visited, right? And then we also put the neighbor nodes into the queue, and so on, and we repeat the process until we hit some final destination or until we visited all of the nodes. So let's get into coding. So the first thing that I'm going to do is I'm going to define a helper function that will help us generate, let's see, what do we want here? We want something to generate adjacency list. Let's call it that. And as always, self. And we'll be passing in a list of word, and that should be it. Yes. Then let's pass for now. Okay. Let's define another helper function called breadth first search, where we'll be passing in our adjacency list, and that's it. We'll be doing this iteratively with a queue. Okay. So the first thing that we have to do is checking to see if n word is contained within word list, right? And the reason for that is because if n word is not within a word list, then that n word is not reachable. Let's see. Right? It's within the problem statement here. Each transform word must exist in the word list. So the n word is a transform word, right? And so if it's not within the list, then we return 0. Yeah, here's another example here, right? The n word is not within the list, so that means no possible transformation to that word. Okay, so we return 0 here. Okay, now, so that's one of our edge cases. So now let's generate our adjacency list. So we'll do self generate, and we'll be passing in word list that also contains begin word, right? We also want adjacency list for the begin word. Okay, so now we'll simply call our BFS, or we also should be passing in target, whatever we're looking for, and this will return true if the target exists within the graph, false if not. Okay, so we'll return, so we simply pass in our list, adjacency list, and target here. So in this case, so let's make the naming consistent. We call it n word, and this will be adjacency something. We'll just call adj for now. Okay, so now let's get to the meat of the algorithm here. So the first thing that we have to do is we have to generate adjacency list, right? So, and what I was saying earlier is that we are using a hash map. So we call it lookup, initialize it to some hash map, empty hash map, and now we're going to iterate to each word within the list. And now we're going to generate unique keys for each transformation. Right, so we do of okay, and what I'll do here is I'll do something like this, where so you might be wondering what I'm doing here is, so let's say for example here we have the word hot. Let's say the word hit, and what as I was saying earlier is this word can be this word has 3 unique transformation by either changing the first character, the second character, and the last character. And essentially with the asterisk we are trying to create a unique key for that transformation, right? By changing the first character, right, we want to associate that transformation to a list of words, right? By changing the first character, how many words are there that can be transformed into, right? And so these will be our unique keys. So, and the reason why I'm doing this is so that so that I'm taking a character out at a time, and I'm adding the asterisk right in the middle. So in Python we are essentially getting a substring from beginning to I, from I plus 1 to the n, right? We want any character to I, right? Let's see. And the second field to the right of the colon is not included. So in this case 0 here, 0 won't be included. And we are doing I plus 1 because we still want I. So I'm just, for example, we still want I to be included. We don't want H to be included. We still want I, and the asterisk will be in place of H. Okay, so that's essentially what I'm doing. I hope that's sort of clear enough for you guys to understand. Okay, so now all we have to do is we simply have to let's make the naming consistent. So we are calling it adjacency list, right? So let's just call it that. Okay, so we are looking the key up. If the key doesn't exist, we'll return an empty list. And finally, once this key value pair is initialized within our hash map, we'll append the word itself to this, right? I forgot to mention here, right? The word itself will also be included within this adjacency list. Let me think about that. Yeah, that's right. So for example here, hit will be included in all of the transformations here. We're also including the original word here. Okay. just, for completeness, let me just put it in our example here. Okay, and finally we'll be returning this adjacency list. Okay, so really that's all we have to do here. So now let's get to BFS, right? So in order for us to do BFS, we'll be also needing a queue data structure. So I'm going to import from collections, and we'll be importing the queue. So the reason why I'm using the queue is that it's optimized for queue and stack operations. And popping and pushing or appending should be all constant. So let's first initialize a queue, and then we'll set the first one to be the begin word, which is something that I forgot to include here. Okay, so we'll include begin word here. Alright, so now the other thing we have to do is we have to, so we'll be popping from this queue, right? So we'll be checking if the size of queue is greater than 0. Actually within the queue, we'll be storing the word and also current distance, right? And we'll set the initial distance to 1. Okay, so now so the first thing that we do within this loop is popping this queue, right? Pop left is actually, because we are using DQ as a queue, we are popping left, meaning we're getting the first element of the queue, DQ, every time. Okay, so now we also have to, another crucial thing here, because this is a graph, we don't want to encounter cycles, we don't want to get into infinite loop, so that's a reason why we also have to keep track of nodes that has been visited, right? So first thing that we do here is we add the word after we are popping left, we add the word to this thing called v, essentially visited, right? We're marking that word as visited. Okay, so now once we got the word, we have to explore all of its possible neighbors, right? And we have this lookup table. So first we have to get the general form, which is the unique key here. What do I mean by general form? I mean the unique key that we have generated here, right? By changing a character. What is a unique form? What is okay, I think you know what I mean. Let me try to write this out first. So we have this word here, and we want to get key, right? This key will allow us to look up all of the possible neighbors of this general character change, right? So as I was doing before here, the key will be like so, and we'll be also exploring all of the neighbors, and so let's make the naming a little more verbose. So we look up the key. So now that we have the key that points us to a general form of transformation, and with that key we are looking up existing neighbors that can be reached, right? the first thing that we do here is we check if the neighbor is in. If it's not in our v, then we add that neighbor, right? Actually, let's make the naming a little better here. Let's call it visited, right? So if this neighbor has not been visited, then we'll put this neighbor within our queue, right? So we just do a pen neighbor, right? And we also have to update our distance for that neighbor, so it'll be our current distance plus 1, right? And we also have to check if this neighbor is the n-word. If it is, then we return right away, because this is the shortest distance. And as I was saying earlier, we are already considering all the paths at the same time, and whichever path reaches the n-word first will be that shortest distance. And here we'll just return dist plus 1, and that's it. Okay, so now in the outside loop here, outside of the loop we return 0. Okay, so let's see if this works. So let's do a quick run. Uh-oh, that's not quite doing what we expected to do. Let's see here. Begin word, end word, word list. So let's print this adjacency list out to see if it's doing the right thing. Let's see. Nothing's printing. Let's see, what are we missing here? Oh, right. If so, that's not right. We're checking to see if n-word is not within word list, then we return 0. So that should fix the problem here. Let's see, lookup is not defined. There might be some inconsistency in naming. So right here. Okay, let's run the code again. Okay, and that should be it for the solution. So let's see if this works, and it works. So let's quickly go over the runtime of this algorithm, just for completeness. So the runtime of this, so BF, as we know, that is O of n, right? Generate key, generate adjacency list, that's what I meant to say. Generating adjacency list takes O of n times k, where k is the length of so let's make this nice, length of string, right? Longest string, or essentially they are all the same size, so it's length of string. And the reason for that is because for each word we are iterating through all of the possible character changes, and all of the possible changes are one character at a time, so it's just the length of the string, k changes essentially. And BFS, just to be precise, is O of n times k, and because there are k possible unique transformations, we are And that's what you see here, right? There are k possible transformations, and the n comes from the number of words that we are visiting. There are only n words, right? Same here, n words. We are going to n words. So this is time complexity. And in terms of space, we are storing a lookup table, adjacency list lookup table. So O of n for the adjacency list as well as the visited set. Okay guys, so I hope this video helps you understand this problem a little better, and see you next time.